Hey everybody, welcome to our first assignment for CS 302. You can see there SpongeBob is also excited for our semester to begin. This assignment is going to be on linked lists, which is really a warm-up and segue from the previous course, which was CS 202. So this will get us sort of back into that C++ mode again. It does incorporate classes, pointers, also involve memory management as well. So a lot of topics, a lot of the important topics from CS 202 will be implemented here for this first assignment. So you only have to worry about just writing the implementation file. You'll be given a header file, and all the test mains you'll be given as well. So you have to just essentially implement the linked list class, and that's it. Now, just as a warning, you will have to use this linked list class to implement some sorting algorithms for a later assignment. But for now, let's go ahead and just focus on this assignment right here. Let's go ahead and now just talk about the actual header file, go over the quick details, and then of course, go over in more detail some of the more complex functions for this class. Okay, so for our linked list class, we have our header guard as always, and we use a template because, well, if you remember from CS 202, a list type structure could really be a list of any data types. You can have a linked list of integers, double, strings, and so forth. So it makes sense to have it as a template. And this linked list class we're going to implement is going to be a two-directional linked list or a doubly linked list. So you can go left to right or right to left, but there's two directions you can take. So here's our linked list class setup, and then we have our first subclass, our class node. Now recall, this node class is going to just essentially, every element of our linked list will be a node. So notice in this picture right here, each of these rectangular boxes is going to be a node object. And each node has these fields, or we can see the sub boxes here. This middle box, that's going to be our data field, where every element in our linked list contains some data. It'll be stored in that middle sub box, or we use this convention just to make it easier for us. This left sub box, that's going to be our previous node, or sorry, a pointer to our previous node. So let's look at this node right here, this middle node. You can see here that this sub box contains a pointer, an address of a location of its left neighbor. So an arrow points to the left neighbor, previous node in the list. This node's that right sub box, every node's right sub box contains an address to the node to the right, or the next node. So for this node right here, this is our data field. Our previous, or prev, contains the address of our node to the left, and then this node's right sub box contains the address of a node to the right. So every node has this. And of course, the head node, the first node's previous would be null because there's nothing to the left of the front. And a tail node's right contains also, tail node's next also contains a null because there's nothing to the right of tail. So that's the idea. And we have our two constructors right here to initialize our node. You don't have to use them, but I put them there to maybe help you with some of the code to make it a bit more simple to code, or for simplicity purposes. Now every element in this class node is a public, so really this is just a glorified struct, but a class does look fancier, so use the word class instead of struct, but it's really just a struct in a sense. So that's really every element of our node, and our constructors we have here are nice because it sets our pointers, everything initializes our data essentially, which is nice. And now with our linked list class, we have our head and tail pointers as shown in this picture. Our head pointer always points to our front node or leftmost node, and our tail points to the end or rightmost node. This class Iterator is implemented for you completely. So I gave you all the code for this. So I will, of course, go over some examples of Iterator later on. But an iterator is just a fancy pointer. So the idea is that pointers allow us to traverse a linked list. But in main, we don't want to really expose the pointers of our linked list because it doesn't really do a good job at encapsulation. The pointers are really kind of private, hidden data. So this iterator will kind of give us the flexibility to traverse the linked list as if we had a pointer in main, but at the same time encapsulates that pointer data within the object iterator. So just for layman's terms for right now, the iterator is going to just really serve as a pointer, but mostly to be used in main to allow us to navigate a linked list freely, but keeping the pointer data private. But I'll go over this in more detail later. Let's go ahead and now talk about these members of our class linked list. So we first have our default constructor, which in the description is given to you. So I do have a description here in this PDF. You, of course, can read through it if you like, but I chose not to read this out here in this video because, well, that would make no sense. So anyway, this default constructor just sets the head and tail to both be null pointer, which denotes that you have an empty linked list. Then you have your copy constructor. If you recall from CS202, you're passing in a linked list object into this constructor, and then you have your this, or your star this object, which is the object that is being created by this constructor. You want to deep copy the linked list. So fairly similar, I'd imagine, from CS202. Then you have your assignment operator, which is again designed for deep copying. So you want to essentially have a linked list 1 equals linked list 2, and you want to deep copy everything from linked list 2 into linked list 1. So let me just write some notes here to help you visualize this. So suppose we have, let's say, a list. I'll use int for right now, and I'll call this L1. Let's say we, insert some content into our linked list. Well, here's what our copy constructor, how it works. We're going to create another list right here, L2, and pass in L1. Suppose L1 contains a set of nodes. This copy constructor is going to deep copy everything from L1 into L2. You have to deep copy it. That's what the copy constructor does. And the assignment operator works like this. Suppose you do more content and you do something like L1 equals L2. So the copy constructor, or sorry, the assignment operator in this case, will take everything from L2 and deep copy it into L1. So L2 will be your RHS right-hand side object, and L1 is going to be your this object. In this context for your copy constructor, L1 is going to be that parameter object, and L2 will be your this object, because L2 is being created by the constructor. In this context, L1 is the object that called this operator function. Then you have your destructor, which is just going to deallocate the entire linked list. So let's go through our simple functions first. So push front, push back. Well, push front is going to be a head insert. Inserts and to the front of your linked list. And I could go over some details of that soon to sort of help you visualize how push front would work. Then push back, same idea, inserts to the back of the linked list. Similar code, but a little bit different. So push back is a tail insert. Pop front removes the front element. Pop back removes the back element. Pretty self-explanatory. The function is empty, which I wrote for you. It returns true if the list is empty and false if it's not empty, which this line of code right there does check that. If head and tail both are null, then it returns true, which means that the list is empty. If head and tail not equal to null, then this would evaluate to false, which would imply the list is not empty. Then we have our tFront, tBack functions, which I gave those to you as well. It returns the head node's data field, and the back returns the tail node's data field. Pretty simple. Then we have a remove node and insert node. So these two I'll have to go into more detail in a little bit, but remove node, basically you want to deallocate a node that the iterator object points to. So for example, if we have some iterator that points to this node right there, then we would call remove node, pass in this iterator, which tells the function to deallocate this node right there. And again, I'll go over iterators and these functions in a bit more detail in a little bit. And then for insert node function, right here, this function inserts a node after a given iterator and is going to assign the following data into that node. So for example, if I called insert node pass and iterate. I pass, let's say, some data value, say 5, for example. This function is going to insert a new node after this node that iterator points to. It'll create a new node after this node and assign 5 into its data field. So this first parameter tells you where you want to insert, which location in the linked list, and then the second parameter will be the actual data you want to insert into that newly created node. And of course, the begin and end functions are given to you. This begin function returns an iterator that points to your head node, and end returns iterator points to the tail node. And then the last function, the swap function, which will be probably the most difficult one to write, will swap two nodes in a linked list. Now, you're thinking, well, from 135, swap is pretty simple, just 2 lines of code. Well, we're going to do some fancy swapping because we don't want to just simply swap the values. But the swap function is going to physically move two nodes in a linked list. And again, I'll go over the details in that little bit, but it's going to require a little bit of pointer reassignments to implement this. So what I'm going to do right now is just go over some of these simple functions in a bit more detail by drawing it here on OneNote to give you an idea as to how you want to implement these functions. And then towards the end, I'm going to go over the swap function. Let's go ahead and just go ahead and cover a few simple functions in more detail next. Okay, so let's consider the following linked list right here. So I think the concept of pushing back and pushing front, that concept is actually not very complicated. But of course, to program this, well, that's a different story altogether. Let's go ahead and just talk a little bit about iterators before we go any further. So the iterator class code is given to you, but you still want to just understand how iterators work. So, for example, if I want to create an iterator, I can do the following. So I'm going to go ahead and just first define the iterator. Iterator, and I'll call it IT. So the iterator class is defined within the linked list class. So notice right here, here's our class LL. Iterator is defined within it. So we have to use list followed by a scope operator that will tell us that, okay, we want to go into the linked list class and we want to access the iterator type. So IT is an iterator right there. Now, in order to traverse the linked list, all we'd have to do is just say IT equals L dot begin. So the begin function returns an iterator that points to the very front. So notice for iterator, if you look at the class, we have this node star current. So the current is a private member in the iterator class. So the way we can think about this is here's our IT. And within our IT object, we have this current pointer within it. And it's going to be assigned to the head node because the begin function returns an iterator whose current points to head, and it's going to copy it into IT. So long story short, IT will point to the head node. But in reality, IT is an object, and within the object, there is a current field, and that current field, which is that pointer instead of IT, is going to point to the head. But I'll make this simpler and just say for now, we'll treat IT almost like a pointer. Essentially, IT points to that first node. Okay, so now we can, of course, retrieve the value in it by calling the star operator function. So I could do something like cout star IT and L. I implemented for you this operator star right here for the iterator class. It returns essentially, in this case, IT is our iterator. It returns IT's dot current arrow data. So it returns the data field of the node that iterator points to. So it returns 3 in this case because IT points to this node right there, which contains 3. So star IT essentially is a dereference operator in a sense. It will dereference this iterator and retrieve the data value. Now, we also want to be able to maneuver through a linked list as well. Well, to do that, we can do one of two things. We can call it and call this a postfix plus plus operator. And a plus plus is given to you. It's going to basically just move the iterator it over to the right. So it's going to set it to now point to the next node in the linked list. And I could, of course, do star it, which returns 8. You also can do plus plus it as well. You can do the prefix version, which are implemented for you in this case. So right here in this class, the operator plus plus with empty parentheses, that's your prefix operator. And then the plus plus with the int after is your postfix operator. So that way you can do it plus plus, or you can do plus plus it. They both are going to do the same thing, sort of. I mean, there's some difference between them, but I guess in 135 you weren't really taught anything too crazy with unary operators, so it shouldn't really make any difference. As long as you don't do anything bizarre, it should just work fine. So the plus plus it moves it over to the right. Now it points to that node. So if you want to move it to the right, plus plus. And of course, you can do it minus minus, or you can do minus minus it. Either one will work. The minus minus is going to move the iterator over to the left. So in this case right here, it points as node 2. It will get reassigned to now point to 8. And so forth. So you can do it equals L dot begin to reassign it to the front. You also can do it equals L dot end, which will assign it to point to the tail node. And then from the head or tail, you can do plus plus minus minus accordingly to maneuver through a linked list. So essentially just acts really as just a fancy pointer, really. So that's a quick crash course on the iterator class, but again, it's implemented for you in a linked list class, so don't worry about it. You don't really have to use this in the linked list class scope, but in main, you will definitely have to use iterators to really maneuver through your linked list. Okay, so now that we got this out of the way, let's go ahead and now just talk about a few of these functions in our linked list class. Okay, so let's go ahead and now talk about the the pushback function. So in this case right here, so suppose we wanted to push back a new node. All right, just a little nicer. Push back. And I'll just say 7. So this function is going to insert a new node to the back of our linked list and assign 7 to this node. So I'm not going to go over all of the actual details, but I'm going to go ahead and sort of draw this out step by step. So the first thing you would have to do is create some temporary pointer. You of course can create pointers inside of the pushback function scope. So you could have iterators if you want as well, but there's no point because in the class, it's a good idea to use pointers. Iterators are mostly really meant just to be used really outside the scope of LL class, like in main. So I would just create a pointer node star temp. Node star temp. And then you have to allocate a node to this pointer. Well, how do we do that? Look up your CS202 nodes. It's very simple. Just allocate a node to this pointer temp. That's sort of 2 lines of code so far. So the next thing is you want to assign to this node, you want to assign 7 right here. Well, how do you do that? Well, you have to first dereference the pointer temp, which if you dereference temp, you can access that node object that temp points to. And then of course you can dereference it. So I'll give you a hint, or not a hint, I'll just give it to you. Remember this error operator from CS202. Equals, and then whatever the parameter is called. That's the star operator, remember, it will dereference the pointer and access a field in that node that temp points to. So then that's your first task. And now you have to sort of wire this linked list up a little bit. So the first step is you want to set tail. You want its next to point to that node right there. So tail arrow next. that's going to reassign this next field. You want to assign it to the same node that temp points to. You almost want to shallow copy these a little bit. And then you want to set temp previous to point to tail. So temp arrow prev will access this previous field, and you want to assign it to the same node that tail points to. Almost doing a shallow copy, because now these two pointers point to the same node. You want to, of course, set temp's next to be null pointer. And the last step is this is going to be your new tail node from now on. So you want to set this, you want to set tail to point to this new node. Well, you just reassign tail to point to the same node temp points to. And that's it, you're done. You have the new node 7 inserted at the back of your linked list. Now, a lot of students like to use the word delete sometimes because they're thinking, oh, okay, because now temp is no longer needed. So I want to delete. I want to wipe out the address that temp contains. But remember, delete is a very bad word in C++ because delete doesn't actually delete. It's a bad word. It's misleading. Delete actually deallocates. If I say delete temp, we're going to essentially deallocate this node that temp points to, which is, how shall we say, not too good if we did that. So if you wanted to clear temp, you could say temp equal null pointer, which will wipe out the address of temp. But we don't want to deallocate the very node we just inserted. Now, temp is going to be essentially a local variable declared in the pushback function. So once the pushback function terminates, the temp, which is locally defined in pushback, will disappear anyway. So you don't have to really worry about temp. Now, for this pushback, there is an edge case to consider. Because what if you have an empty linked list and you push back? Well, you have to make sure that if you do insert a node to an empty linked list, then head and tail are both going to point to that one node. And the reason why is because if you only have one node in your linked list, that's both your front and back node at the same time. So you want to have maybe an edge case to consider. If you have empty linked list, then you have to do a little bit of difference. If you have a non-empty linked list, then you do this generic code I just showed you right here. Now, for push front, it's fairly similar, just on the opposite end of the linked list. So nothing too complicated there. So let's go ahead and now cover the pop. Let's do pop front function, why not? So for pop front, we would call it like this, L dot pop front. So pop front essentially is going to remove the first node in our linked list, which is that node 3, and then head will now be assigned to the new front node. So again, what you can do is you can just maybe set up another temporary pointer, a local variable you can define in the pop front function, set temp equal to the head. And then the next step is you want to move the head pointer over to the right by 1, which shouldn't be too bad, or a little review from CS202. Because the end result is that this head pointer is going to now point to the second node of your linked list. That's going to be your new head. And now what you want to do is you want to cut this node off from the linked list. So you want to set the head previous, or now the head points to this node 8, you want to set the previous now to be null. So now it can't be really reached from the head node anymore. So now 3 cannot be reached. Now you have temp, and now in this case you do want to deallocate because you want to essentially destroy, not destroy, but you want to recycle this node back to the system heap. So you want to then deallocate or delete temp, which would essentially deallocate this node, which would essentially wipe it off. Essentially, it would disappear. And end result is you have linked list right there. Without that first node that was there before, now it's gone. So again, for pop back, it'll be fairly similar, except on the opposite end of the linked list. Now you have to also consider an edge case, because for pop front or pop back, if you only have one node in your linked list, then pop front and pop back, the result is going to be an empty linked list. So you have to have maybe possibly different logic for a case if you have one node or you have more than one node. But again, it's very simple to check if you only have one node. If head and tail both point to the same node, then your linked list only has one node in it. Okay, let's go ahead and now just maybe discuss a little bit of the iterator insert and remove. And then, of course, we'll then talk about the mighty swap function. Okay, so given this linked list right here, suppose we did a bunch of push back and push fronts to generate this linked list right here. And suppose we have iterator, we set iterator equal to L.begin. So I'll write the code here. So suppose we did something like this, it equals L.begin, and then we did it plus plus to be in this situation right here. So there's now a function to insert into a linked list. So suppose we did the following. We would do something like L.insert node. We pass in the iterator it, and I'll pass in 5. This function is going to insert a node whose data value is going to be 5 right after it is the end result. So just like from CS202, remember how this works. We can of course define a temporary pointer temp within our insert node function. We can allocate a node. I think I'll put it like this maybe. Yeah, it's gonna work. We set that temp node's data value to be 5. Remember, dereference temp. So temp arrow data, assign it with that second parameter in this function insert node, which will assign 5. Then remember what we have to do. We have to essentially have this node that it points to. You want its next to point to temp, this temp previous point back to it. And we have to also make sure that temp's next points to the node after it, which is this node right there. And then node after it points back to temp. So it's going to be 4 lines of code, 4 assignments. So you have to essentially one by one. So the order actually does matter. So let me just go ahead and just do this. So the order is actually going to matter, or you can define additional pointers. So if you want, you can define another pointer. I can call this maybe just X and assign it to the node after it to make life a little bit easier. And now actually then the order now is not going to matter anymore for this part. So the first thing you would do is set the node that it points to, set that node's next to temp. Temp previous assigns to the node that it points to. And X currently is the node, at the moment at least, that was after it. So you set X's previous to temp, and then temp's next points to X, and then you're done. And of course, after this, you don't have to deallocate anything because since temp and X were both defined locally in your function body, you don't need to actually do anything because temp and X will be deallocated. The only edge case to consider here is it could happen to point to the tail node, and then if you do the insert, you're essentially doing a pushback. So you can just call pushback actually in this function insert node. Now the last thing I'm going to cover for iterators will be the remove function. So let me go ahead and just now wipe all this out and start over again for the remove function. So suppose we did now, instead of insert node, we would do L dot, I think it's called remove node. Like this. So remove node means you want to deallocate the node that it points to, is the idea. And in this case, what we're going to do is you have to deallocate this node 3, or this node right here. And you want to set it to point to the node after. So essentially, in this case, if you were to remove this node, we deallocate this, and the iterator needs to be assigned to the node over the right, the next node. So we want IT end result to point to this node right there. So to do this, of course, you can create some temporary pointers as requested. So what you can do is you can create 2 pointers, maybe have like X and Y to surround IT. And it'd be very simple you can create 2 pointer variables, and X would be set to the left of IT, and Y is to the right of IT. So very simple to set X and Y pointers up like that. And now what you have to do is make it where X points, X is next, because you want now this node to now jump over IT, now point to Y. And you want Y's previous to point back to X. So now this node jumps over 3, and this node also jumps over 3. So this node's next goes to 2, and 2's previous goes to 4, essentially making 3 unreachable now in our linked list. And then we want to deallocate this node. And then we can just reassign IT to point to Y. And that's it. That's all the remove node function does. And again, there are some edge cases to consider, because IT could point to the head or it could point to the tail. So there are a few cases to consider in this code, but that's the only thing to consider really. So I gave you kind of step-by-step work. Now, of course, you have to take what I gave you and be able to generate code for it, but every pointer reassignment was one C++ statement. You had to either set X, next, Y previous, Y arrow previous, Y arrow prev, sorry. So that's all there is to that. So that's sort of the bulk of the class. So now let's go ahead and talk about the swap function. Okay, so let's consider this linked list right here. So let's say we have a bunch of, we did a bunch of push back and push fronts to create the linked list that you see right there. And suppose you have I and J iterators, you set I and J to the begin, and you did I and J plus pluses, and I, J. So you got it where you have the linked list in this formation. I points to this node, J points to that node. And now we're going to call swap, and we pass now our 2 iterators. So for this function, you can assume that the way it's going to be called, that the I iterator is always going to come before the J iterator in the linked list. Now, I and J could be adjacent to each other, or they could have some distance from each other. Either way, I will always appear to the left of J. So in this scenario, I and J are not adjacent. So you have to consider a few cases. So one case is if I and J are adjacent, you may have different code versus when I and J are not adjacent. Now, an easier way to implement swap would be just to simply swap data fields. Just put 3 over here, 7 over here, and that would be it. Very easy. But, that would be too simple for our linked list assignments. You have to, of course, complicate this a little bit. So what we're going to do is not just swap these data fields, but we're going to do essentially this in long term, or long story short, we're going to do this. We're going to pick up this node, pick it up, and we're going to take this node, pick it up, and drop it here. And we're going to drop this node right here. Of course, I kind of didn't copy it really perfectly, but you get the idea. We physically pick up those 2 nodes and move them geographically in the linked list is the idea. And at the end, after you do this, you want to make sure that I still points to the second node of the linked list. You want J to still point a second to the last. You have to then swap the I and J current pointers the regular old-fashioned way to make sure I still points to the same spot in the linked list and J still points to the same spot in the linked list. That's the idea. However, to implement this is a little bit tricky. So let's go ahead and just see if we can sort of reverse this. Perfect. Okay. So here's the original linked list. So to do this, I guess we can think about the episode from SpongeBob where I think Mr. Krabs was trying to go out with Mrs. Puff. And then, Mr. Krabs was saying, we're not talking about this or this. We're talking about this, that whole thing. And SpongeBob at one point was going nuts. Like, we're not talking about this or this. We're talking about this. And he just goes nuts on screen. I mean, if you ever saw the episode, you know what I'm talking about. So it's going to feel a little bit like this when you implement this swap function. So essentially, here's how we can think about this. So I and j, or this node 7, this node 3, they're not just here by mistake. They're here in context. So the thing is that 7 is in this location because the node to the left of 7, 5, points to 7. 7 points back to this. So this node's next points to this node, and this node's previous points to that node. And also for 7, its right neighbor points back to 7, and 7 points to the right neighbor. That's how 7 is in this location. Same thing for this node right there for 3. 3 is in this position because of its neighbors. So 8 points, or this node's next points to 3, and this node's previous points to this node right there. And same idea, this node's next points to that node, and that node's previous points back to 3. So that's kind of how these nodes are in these locations. So to fix this, or to actually swap these, here's our first step. So in order for 3 to be in this location, 5 has to point to 3, 3 points back to 5. 3 has to point to 2, 2 points back to 3. And then essentially, 3 is going to really slide in between 5 and 2, essentially. So here's what you have to do. So you're going to essentially reassign this pointer. Okay, I don't know why it keeps doing that. One note here. I don't know why it does that, but I'm going to try my best. Okay. Been acting up one note today. There we go. So we want to have it where 5 is going to point to this node, and then 3's previous points to 5. And then we want to do is, since 2, this node 2 right here, this node was actually the right neighbor of 7, it has to point back to 3, and then 3's next. Okay, it's a little too much. A little bit difficult to erase for some reason. Okay, try this one more time. I don't know why. This must be a new feature on OneNote. So like if you try to delete right there to pen, it just highlights the entire. Okay, and then 3 has to now point to 2. Now, if you were to pull on the head and tail pointers, or actually if you were to pull on, I guess maybe the 5 and 8, it would actually force 3 in between 5 and 2. So if you look at this, 5 points to 3, 3 points back to 5. 2 points back to 3, 3 points to 2. So essentially this node 3 is actually, if you were to redraw this, is actually between 5 and 2. So 3 has now moved in this position. So we're almost there. Now 7 has to move where 3 used to be. To do this, well, we have to actually have it where 7 has to point to the neighbor of the old neighbor of j, which was 3. So 7's next. Let me just try to use a different colored pen for this. 7's next has to point to the tail, or to the node that comes after j. It happens to be tail. It's not going to always be the tail node, but happens to be in this case. And then the node that came after 3 is previous, has to point to 7. And then the node that came to the left of 3 originally was 8. Well, 8's next has to be assigned to 7. And then 7's previous points back to 8. Ooh, I'm actually getting a little bit lost, but I think it's correct though. So there we go. So now if we were to take the head and tail nodes and tug them apart from each other, you would see that 3 would slide between 5 and 2, and 7 would actually slide between 8 and 1. Essentially, it would swap those two nodes geographically in the linked list. Now, when you do this, however, the I and j also moves with the nodes. So after you perform this work, you want to make sure that you set I to point to the node. So let's say in this case happen to be a second node. You want I to still point to the second node. So this node 3 is your new second node, and 7 is your new second to last node. So you want to make sure you also swap the I.current and j.current pointers to point to the new positions, because you want to make sure they still point the same location in the linked list. Now, of course, there are a few edge cases to consider again. So you could have where I and j could be non-adjacent. I and j could be adjacent. Also make sure, what if I points to the head and or j points to the tail? That's going to create some additional, we don't have to do anything different, but you have to reassign the head and tail after. So imagine that, let's say I happen to point to the head node. After you do the swap, I and the head are both going to move. So you want to reassign I and head. You want to reassign head to point to the now new head node. Because let's say, for example, if we had it where if I was pointing to this node 5, and we want to swap 5 and 8, let's say, what happens, 5 would move here, 8 would move in this position, but the head pointer also moves. So you want the head to now point to the new head node afterwards. I hope that makes sense. So this one's a little bit of gonna be a real pain to work with, but I actually do provide you with a lot of main files, and they almost act like unit tests, where it tests out different parts of your class, and each case in a swap note have a separate main for each of them. So I'm trying to make it not all or nothing for this assignment. Let's go ahead, look at the files provided and the main provided as well, and to show you how to compile it and how they should run and so forth. Okay, so in the zip file that I provide for you, I give you the skeleton code, which is essentially I give you the header file, which is right here, same as in the PDF. And I also give you the LLCP file, but it's sort of the, there's a skeleton file, so you have to write your code here, but I do provide you with the complete function headings and so forth, so to make the compilation a little bit easier. And of course, I have these at the very end. It's a weird template thing, because since I have the implementation header file separated, in order for templates to compile correctly, you have to define them right there at the end of your implementation file. So you have to write your code here. You have to submit just your ll.cpp file only. Everything else will be already in code grade. So here's one of your test files to work with. So I create a list object right here, say the string type, and I push Homer, Bart, Maggie. I push Maggie to the front, Lisa, Marge. These are Simpsons characters. They were a good cartoon back in the old days, but sadly, Simpsons aren't what they are anymore, but that's okay. They were once a good cartoon. So over here, we're testing out the push functions. I simply have these two loops right here to iterate and traverse through our linked list. The auto keyword is just a shortcut, so it essentially just sets iterator to point to the front of your linked list. And I have a nil iterator, which is a null, kind of like a null pointer, if you will. IT++ is an iterate through your linked list and so forth. Now, to get this to compile, we just do G++, we have ll.cpp, and we want to compile the push test function. So ll push, let's see what happened there. Push test, okay, there we go. So I use tab to autofill, but anyway, so there we are. That will compile into an a.out file. And then of course, /a.out, we'll run it on Linux. And there's your output, so it should match this. So one of our test code for code grade will look like this. Our other main files that we have, let's see, what else can we also test here? We can also test out the iterator insert test. Here's the code given to you for that. So basically here, I create a few iterators. I push back several names. I output the list before. I set IT to the front, move it a couple of times to the right. And I want to insert Dr. Hibbert. So it looks like IT points to the first node, second, third, fourth. So we're going to insert Dr. Hibbert after the fourth node in the linked list is going to be the idea for this. Let's go ahead and test this out. So to compile it, once again, g++ ll.tpp, just like in CS202, and ll iterator test. Sorry about the noise. Why isn't it? Let me see, did I spell it incorrectly? Iterator test. See what's the problem here. Oh, iterator insert test. My mistake. I'm sorry. Insert test. There we go. And we'll try the first one. Okay, there we go. So again, I just take the LL file, the implementation file, space with the main I want to test it with. It's going to compile link him to one a.out file, /a.out. I run it, and that's the output your program should generate if it was written correctly. So let's take a look. So in our list, 1, 2, 3, 4 was Marge. Dr. Hibbert should have gone after Marge. And there we are. So 1, 2, 3, 4. We insert Dr. Hibbert after Marge, which, yep, there it is. If you go from right to left, in this case, same thing. 1, 2, 3, 4, and then Dr. Hibbert is right there. So there we are. So basically, you can just test out each main just like that. G++, name of the implementation file, and then link it with the appropriate main, and then run it. There's no input. Everything is just going to be given to you in these main files. And on code grade, it will test with the same exact files. So essentially, as you can see here, here's a skeleton code. So here's the files that are given to you. And I also provide you with a set of the outputs as well. So you can just check your outputs also locally. But again, on code grade, it's going to just compare all your output to the output file is provided right here for you. So that's essentially the end of the overview of the assignment. Hopefully this helped you with everything. So I guess happy coding, and till next time.